What is a function? Now, one definition of a function is that a function is a rule that maps one unique number to another unique number. So in other words, if I start off with a number and I apply my function, I finish up with another unique number. So for example, let's suppose that my function added 3 to any number. I could start off with the number 2, I apply my function, and I finish up with the number 5. Start off with the number 8, and I apply my function, and I finish up with the number 11. And if I start off with the number x, and I apply my function, I finish up with the number x plus 3. And we can show this mathematically by writing f of x equals x plus 3, where x is our input, which we often call the argument of the function, and x plus 3 is our output. Now suppose I had an argument of 2. I could write down f of 2 equals 2 plus 3, which gives us an output of 5. Suppose I had an argument of 8. I could write down f of 8 equals 8 plus 3, which gives me an output of 11. And suppose I had an argument of minus 6. I could write f of minus 6 equals minus 6 plus 3, which would give me minus 3 for my output. And if I had an argument of z, I could write down f of z equals z plus 3. And likewise, if I had an argument of x squared, I could write down f of x squared equals x squared plus 3. Now, it is worth me pointing out here that although at first sight it might appear that we can choose any value for our argument, that's not always the case, as we shall see later. But because we do have some choice on what number we can pick the argument to be, this is sometimes called the independent variable. And because our output depends on our choice of arguments, the output is sometimes called the dependent variable. Now, let's have a look at an example. F of x equals 3x squared minus 4. Now, as we were saying before, x is our input, which we call the argument, and that is the independent variable. And our output, which is 3x squared minus 4, is our dependent variable. Now, we can choose different values for our argument, which is often a good place to start when we get a function like this. So, f of 0 will give us 3 times 0 squared, take away 4, which is 0 minus 4, which is just minus 4. If we start off with an argument of 1, we get f of 1 equals 3 times 1 squared take away 4, which is just 3 take away 4, which gives us minus 1. If we have an argument of 2, f of 2 equals 3 times 2 squared take away 4, so which is 3 times 4, which is 12, take away 4 gives us 8. And as I said before, there's no reason why we can't include a negative argument. So if I put f of minus 1 in, we get 3 times minus 1 squared, take away 4, which is 3 times 1, gives us 3, take away 4, gives us minus 1. And f of minus 2 would give us 3 times minus 2 squared, take away 4, which is 3 times 4, which gives us 12, and take away 4 will give us 8. So what are we going to do with these results? Well, one thing we can do is put them into a table to help us plot the graph of the function. So if we do a table of x and f of x, the values we've chosen for our x column, which is our argument, are minus 1, minus 2, 0, 1 and 2. So minus 2, minus 1, 0, 1 and 2. And the corresponding outputs are 8, minus 1, minus 4, minus 1, and 8. And we can use this, as I said, to help us plot the graph of the function. So just to copy the table down again, so we've got it handy. We had minus 2, minus 1, 0, 1, and 2. 8, minus 1, minus 4, minus 1, and 8. So we plot our graph of f of x on the vertical axis, which is our outputs, and our arguments on the horizontal axis. Okay, so we've got 1 and 2, minus 1, minus 2. Okay, we've got minus 1, minus 2, minus 3, minus 4, and going up to 8. 1, 2, 3, 4, 5, 6, 7, and 8. So our first point is minus 2, 8. So we can put that up here. Our second point, minus 1, should appear down here. 0 and minus 4, which will appear down here. 1 and minus 1, appear over there. And 2 and 8, which will appear up here. And we can see we can draw a smooth curve through these points, which will be the graph of the function. Okay, now why are we drawing a graph of a function? Because this is quite useful to us, because we can now read off the output of a function for any given argument straight off the graph without the need to do any calculations. So, for example, if we look at 2, an argument of 2, we know that's going to give us 8. We've already worked that out. But if we looked and we wanted to figure out what the output would be when the argument was 1.5, if we follow our line up and across, you can see that that gives us a value between 2 and 3 for the output. And if we substitute in 1.5 back into our original expression for the function, you can see it actually gives us an exact value of 2.75. Now, earlier on when I discussed uniqueness, I said that a unique input had to give us a unique output. And by that, what we mean is that for any given argument, we should get only one output. One of the benefits of having a graph of a function is that we can check this using our ruler. If we line our ruler up vertically and we move it left and right across the graph, we can make sure that the ruler only ever crosses the graph once at any point. And as we can see, that's clearly the case in this example. And when that happens, the graph is a valid function. Now, if we had the example f of x equals root x, a good place to start is always to substitute in some values for the argument. So, f of 0 just gives us the square root of 0, which is 0. F of 1, so an argument of 1, will give us plus or minus 1 for the square root there. F of 2 will give us plus or minus 1.4, just to one decimal place there. F of 3, which gives us the square root of 3, gives us plus or minus 1.7. And f of 4 will give us square root of 4, which is just plus or minus 2. Now, if we try to put in any negative arguments here, you can see that we're going to run into trouble because we have to try and calculate the square root of a negative number. And we'll come back to this problem in a second. But for now, let's plot the points that we've got so far. So if we take our f of x axis, vertical again, and our argument axis, x, horizontal. We've got 1, 2, 3, 4. And on our vertical axis we have -1, -2, +1, +2. And the points we've got, 0 and 0, 1 and +1, and also 1 and -1. We've got 2 and +1.4, so round about there, and also 2 and -1.4. We've got 3 and +1.7, and we've got 3 and -1.7. And finally we have 4 and +2, and 4 and -2. Okay, and we've got enough points here that we can draw a smooth curve through these points. To get something that looks like this. Okay. Now, as usual, we will apply our ruler test to make sure that the function is valid. And you can see straight away that when we line up our ruler vertically and move it across, for any given positive argument, we're getting 2 outputs. So obviously we need to do something about this to make the function valid. One way to get around this problem is by defining root x to take only positive values or 0. This is sometimes called the positive square root. So in effect, we lose the bottom negative half of this graph. And obviously we also have the issue of the negative arguments. And since we can't take the square root of a negative number, we also have to exclude these from the x-axis. Now, when we start talking about these kind of restrictions, it's important that we use the right kind of mathematical language. So the set of possible inputs is what we call the domain, and the set of possible outputs is what we call the range. So in this case, when we've got our f of x equals the square root of x, we need to restrict our domain to be x is more than or equal to 0, because we only wanted the positive values and 0. But we also notice that now, because we've got rid of the bottom half of the graph, the only parts of the range which are including are also more than or equal to 0. So our range is defined by f of x more than or equal to 0. So now we have a valid function. So what we'll do now is just look at a couple more examples to pull together everything that we've done so far. And we'll start with this one. Let's look at the function f of x equals 2x squared minus 3x plus 5. Now, as usual, a good place to start when you get a function is to substitute in some values for the argument. So let's start with that. So an argument of 0 would give us f of 0, which is 2 times 0 squared minus 3 times 0 plus 5, which is just 0, take away 0, plus 5. So we get an output of 5 there. If we had an argument of 1, we get 2 times 1 squared, take away 3 times 1, plus 5, which gives us 2 times 1 here, which is 2, take away 3 times 1, which is take away 3, and plus 5. So 2 take away 3 is minus 1, plus 5 gives us 4. Okay, if we look at an argument of 2, we get 2 times 2 squared, take away 3 times 2, and plus 5, which gives us 2 times 4, which is 8, and take away 3 times 2, which is take away 6. And don't forget our plus 5 at the end. So 8 take away 6 is 2, plus 5 gives us 7. Okay, if we look at an argument of 3, f of 3 gives us 2 times 3 squared, take away 3 times 3, and plus 5. So this is 2 times 9 here, 18. Take away 3 times 3, which is take away 9, and plus 5. So 18 take away 9 is 9, plus 5 gives us 14. And last but not least, we can also include a negative argument. So we'll put a negative argument of minus 1. So f of minus 1 gives us 2 times minus 1 squared. Take away 3 times minus 1. And of course, our plus 5. So 2 times minus 1 squared just gives us 2. Take away 3 times negative 1, which just gives us a plus 3. And then we've got a plus 5. 2 plus 3 plus 5 just gives us 10. And what we can do is, as before, just put this into a table to make it nice and easy to make a graph of the function. So we put it into a table of x and f of x. And for our arguments, we had minus 1, 0, 1, 2, and 3. And for our outputs, we had 10, 5, 4, 7, and 14. Okay, so let's do a graph of this function then. We start off with our f of x on the vertical axis, as before, and our argument x on the horizontal axis. And we've got over to minus 1 there, 1, 2, and 3. And on the vertical axis, we'll go up to 15. Okay, so our first point to plot is minus 1 and 10, which will give us something there. 0 and 5, which is a point here. 1 and 4, which gives us a point here. 2 and 7, which will be around here. And 3 and 14, which will be about here. So we can see the kind of shape that this function is starting to take here, and we can draw in the graph. What we want is to say that every input gives us only one single output. So we can get our ruler again and just quickly check by going along, and we can see that as we go along, our ruler crosses the curve once and once only, which means that this function is valid. However, an interesting point to note is this point here, the minimum point, which actually occurs when x is 0.75. So with an x value of 0.75, our output can take a minimum value of 3.875. So this means when we look at our domain and range, we need to make no restrictions on the domain because our function was valid. However, our range has a minimum of 3.875. So we write this as f of x equals 2x squared minus 3x plus 5, and the range f of x has to always be more than or equal to 3.875. So, for the next example, what would happen if we had a function f defined by f of x equals 1 over x? Well, as always, the first stage is to substitute in some values for the argument. So if I put f of 1, the argument is 1, so 1 divided by 1 just gives us 1. If I put f of 2, we just get 1/2. F of 3 gives us 1/3. And f of 4 will give us 1/4. And as before, we can also look at some negative arguments. So if I look at f of minus 1, so we get 1 divided by minus 1, which is just minus 1. F of minus 2 is 1 divided by minus 2, which just gives us minus 1/2. F of minus 3, same thing, will give us minus 1/3. And f of minus 4 will give us minus 1/4. Now, if we look at f of 0, we have 1 divided by 0, which is obviously a problem for us. And because of this problem, we have to restrict our domain so that it does not include the argument x equals 0. So let's have a look at what the graph of this function actually looks like. So as before, f of x on our vertical axis for the outputs, and our argument x on the horizontal axis. Okay, so we've gone over here 1, 2, 3, and 4, and minus 1, minus 2, minus 3, and minus 4 over here. And as we go up, all the way up to 1, down to minus 1, let's put the halves in as well. So we've got 1 and 1. We've got 2 and 1/2. 3 and 1/3. 4 and 1/4. We've got minus 1 and minus 1. Minus 2 and minus 1/2. Minus 3 and minus 1/3. And minus 4 and minus 1/4. Okay, and obviously we've excluded 0 from our domain, as we said before. So if we join these points up in a smooth curve, we get something that looks like this. Now, obviously we've excluded x equals 0 from our domain, but it's also worth noticing here that there's nothing at the output of f of x equals 0. So that also ends up being excluded from the range. So we actually end up with f of x equals 1 over x, and we've got x not equal to 0 from the domain, and also in the range f of x never equals 0 either. But what's actually happening at this point, x equals 0? When the argument is 0, what is going on? Well, let's have a look. And we'll start off by having a look at what happens as we get closer and closer to 0. Now, if we start off with a value of 1, f of 1, and remember f of x was just equal to 1 over x, f of 1 just gives us 1. So if I get closer to 0 again, let's look at f of 1/2. That's 1 divided by 1/2. So it's 1 over 1/2, which just gives us 2. So what about f of 1/10? That just gives us 1 divided by 1/10, which gives us 10. F of 1 over 1,000 will just give us 1 divided by 1 over 1,000, which gives us 1,000. And what about 1 over 1 million? So f of 1 over 1,000,000 is actually just in the same way as before, just going to give us 1,000,000. So we can see that as we get closer and closer to 0 from the right-hand side, as we saw on our graph before, we're getting closer and closer to positive infinity. So the graph goes off to positive infinity there. But what happens when we approach 0 from the left-hand side? Well, let's have a look. F of minus 1 just gives us 1 divided by minus 1, which is minus 1. F of minus 1/2 is going to give us 1 divided by minus 1/2, which just gives us minus 2. F of minus 1/10 is 1 divided by minus 1/10, which just gives us minus 10. And we can kind of see a pattern here, okay? So f of minus 1 over 1,000 will actually give us minus 1,000. And f of minus 1 over 1,000,000 actually gives us minus 1 million. So you can see that as we approach 0 from the left, our output approaches negative infinity, and as we approach 0 from the right-hand side, our output approaches positive infinity. And these are very different things. Okay, for the last example, I'd just like to look at the function f defined by f of x equals 1 over x minus 2 all squared. So, as always with the examples we've done, it's worthwhile starting off by looking at some different values for the argument. So we'll start off with an argument of minus 2. So f of minus 2 gives us 1 over minus 2 squared, which gives us 1 over minus 4 squared, which is 1 over 16. F of minus 1 will give us 1 over minus 1 minus 2 all squared, which gives us 1 over minus 3 squared, which is 1 over 9. Now f of 0, argument of 0, will give us 1 over 0 minus 2 all squared, which is 1 over minus 2 squared, which works out as 1/4. And f of 1 will give us 1 over 1 minus 2 squared, which is just 1 over minus 1 squared, which gives us just 1. Okay. F of 2 gives us 1 over 2 minus 2 all squared, which gives us 1 over 0, which presents us with exactly the same problem we had in the previous example when we had 1 over x. And so we have to exclude x equals 2 from the domain. F of 3 gives us 1 over 3 minus 2 all squared, which is 1 over 1 squared, which just gives us 1 again. F of 4 gives us 1 over 4 minus 2 all squared, which gives us 1 over 4. F of 5 gives us 1 over 5 minus 2 all squared, which gives us 1 over 3 squared, which is 1/9. And finally, f of 6 gives us 1 over 6 minus 2 all squared, which is 1 over 4 squared, which works out as 1 over 16. Now, if we want to plot the graph of this function, we'll probably need to put this into a table first. So, as usual, do our table of x and f of x. Okay, and we went from minus 2, minus 1, 0, all the way up to an argument of 6. And the values we got for the outputs, 1 over 16, 1/9, 1/4, and 1, 0, 1, 1/4, 1/9, and 1 over 16. So, if we plot that onto the graph as before, so we have our arguments going along the horizontal axis and our outputs going along the vertical axis. We've gone from minus 1 and minus 2 over there, 1, 2, 3, 4, 5, 6, along this way. And then going up, we've gone to 1 up here. So we're putting a few of the marks. 1/2. Let's put in 1/4 there. Let's put in 3/4. Okay, so we've got minus 2 and 1/16, which is going to come in down here. Minus 1 and 1/9, which will come in over here. 0 and 1/4. Over here, 1 and 1, right the way up here. 2, and obviously this was the divide by 0, so we couldn't do anything with that. We've excluded that from our domain. 3 and 1 up here, 4 and 1/4 down here, 5 and 1/9, and 6 and 1/16. And because we've excluded x equals 2 from our domain, put a dotted line there to show that's an asymptote. And we can draw our curve up through the points, down this side. And we can see, differently to the other example where f of x was 1 over x, this time, as we get approached to from both the left and from the right, both of the outputs are heading towards positive infinity. So a little bit different. And also, because we've excluded x equals 2 from the domain, our function is now valid. But we must also notice that our range is never 0 and is also never negative. So to write this out properly, we have our function f of x equals 1 over x minus 2 all squared. And we've said that our domain is restricted, so it doesn't include 2. And our range is always more than 0. Okay, so let's just recap on what we've done in this unit. So firstly, the definition of a function. And that was that a function is a rule that maps a unique number x to another unique number, f of x. Secondly, was the idea that an argument is exactly the same as an input. Thirdly, we looked at the idea of independent and dependent variables. And we said that the input, x, was the independent variable and the output was the dependent variable. Fourth, we looked at the domain, and we said that the domain was the set of possible inputs. And finally, we looked at the range, and we said that the range was the set of possible outputs. So now you know how to define a function and how to find the output of a function for a given argument.